So, welcome to my dear student. This is regarding active harmonic filter. So, this is to just show you how the already we have discussed about harmonics. Harmonics is nothing but along with any uh, fundamental frequency. If the other frequencies existed, so basically that is called the harmonics. Sometime for rotating electrical machinery like induction machine and all, this harmonic creates a very big difficulties. Like if it is a third harmonic, say you are considering the third harmonic. The third harmonic means so the phase A, it will be at 0 degree. Phase B, it will be 120 degree apart from A phase, and phase C will be 240 degree apart from phase A. Now in case of third harmonic, means it is the 3 times of the fundamental. So first A phase angle is 0, B phase angle is B phase angle is 120, and C phase angle is 240. Now it will be multiplied by 3. So 0 into 3 is equal to 0 degree. Then 120 into 3, 360, that is also in 0 degree. And 240 into 3, it is 720. Means 2 times rotated, and again it is falling in 0 degree. So those are an everything. In case of third harmonic, it is coming to um, uh, all the signals, they'll come and fall in 0 degree. It's a zero sequence. What will happen? We know to create the rotating magnetic field in the stator space, we need all the 3 phases will be balanced and it will be 120 degree aparted. So in case of any due to any reason, if this third harmonic appears, then all the 3 phase, it will come and fall in the phasor will fall in the same at 0 degree. So this will oppose the uh, this will oppose to create the rotating magnetic field in the stator space. This will in turn create the opposition force for the electromagnetic torque that will reflect in the final rotor output. Your torque will reduce, or you can get the pulsating torque, some jerking, and all these things. So it's very difficult. I mean, we need to avoid all these things. Okay. Not only this, in case of any say when the load is nonlinear, so it will inject harmonic in the significant harmonic in the input side. Say you are connecting in my home appliance, there is some inverter or something kind, this some nonlinear, most of the loads are nonlinear in nature. So what will happen, this will inject some nonlinearity in the grid also. So that's why once you are connecting your solar cell or inverter or something like that, then the grid people, they will come and inspect and they will tell you whatever inverter you can use, it is no issue, but your harmonic should be your harmonic should not increase more than 10% or 5%. They will decide like this in every power plant also, because um, uh, this power plant having so many other sophisticated equipments that may disturb your input source itself, get disturbed due to this harmonic. So to avoid this harmonic, there's a very simple methodology. It's a robust methodology, rugged, not robust, rugged methodology, that is use of a simple LC circuit or something like that, or RLC circuit. For a RLC circuit, there will be a resonance frequency. So for a LC circuit, your omega 0, or the resonance omega 0 is equal to 2 pi f0 is equal to 1 by root over LC. That means if you fix the value L and C such a way that the F, whatever formula I told, 2 pi F is equal to 1 by root LC, say the F is equal to 150 Hertz and your L is equal to say 1 millihenry, and using this formula you calculate the C, and that kind of LC circuit, if you add in any electrical source or electrical system where 150 hertz is existed, so through that particular branch, this, as the resonance frequency is 150 hertz and you calculated L and C based on that, then this entire 150 hertz, it will be drained through that particular branch. This methodology is called passive harmonic filter. So like that you calculate several, say what I mean to say this is some source, sorry, say this is some source, and this is connected with some load. Okay, say this is your load. So this load is giving some harmonics here. So this is your source. Due to connection of this load, it's giving some harmonics. Say that harmonics are, actually this is my fundamental. Rather than that, when I am connecting this nonlinear load, it is giving the frequency of F1, F2, and all these things. Some frequencies are giving. So how to find out that? That is done by the Fourier series expansion. Already I explained. You take a signal, then you expand into Fourier series. So the average value A0 in the Fourier series, there is a term called A0, that is the average value or the DC value. Then there will be a term A1 and B1, then A2 and B2. So let us say H1 is equal to root over A1 square plus B1 square. So this H1 will be the magnitude of the fundamental frequency. Then H2 is equal to root over A2 square plus B2 square, that is the second harmonic, and H3 is equal to root over A3 square plus B3 square. So that will be the third harmonics, and so on. Using this simple Fourier series expansion, you can find out the existence of various harmonics in the uh, system, as well as its magnitude. Okay. So say similar way you observe that after connecting the nonlinear load, rather than this fundamental frequency F, you having this F1 and F2 in the circuit. So you design two LC circuit. This is L, this C, then one more LC circuit, and you connect it to ground. So this branch resonance frequency is F1 and this branch resonance frequency is F2. So what is this? This is uh, uh, 1 by omega, that is 2 pi root over LC. Say you take L2 C2. So sorry, L2 and C2. So this is your L2 and this is your C2. And your F2, say I want to drain 150 hertz and you take your L2 as 1 millihenry. So here in place of L2 you put 1 millihenry and calculate the L2, that is your C2. Okay. So this is called your passive filter. So like that, how many, because it is very easy to design and it is a rugged design, but this is applicable for a specific system. Hmm. You cannot use this any other system. So the number of LC, all these branches, it will be more. So this is called passive harmonic filter. Another technique is there when the power electronics and this um, high frequency switching semiconductors are invented. So that is called the active harmonic filter. So just I'll show you one simple active harmonic filter I made for you. So you see this is your source side, and here is the line choke or something like that. I have used this value, and this is a simple three phase rectifier, and that load is connected here. It is uh, 0.3 uh, 0.00, so this much Henry, and this is a capacitor 0.747 millifarad, and this is a load or this. So this entire rectifier along with this, it's a nonlinear load. So the same thing I have connected here to show you the comparison. And another additional power in electronic circuitry I have used here. This is basically a inverter. Okay, this is a three-phase inverter, and this is also for the isolation. It is point. This value is given as 0.002. This is arbitrarily I calculated, and this one. And here is your one RLC branch. So this your sorry, RC branch for filtering and all. So this is 0.1 and 2 microfarad. This all these things are calculated based on this particular these things. I'm not explaining that one. And this inverter is getting switched. How? I am capturing the current which is drawn due to this nonlinear load. You see, this is IA. I am taking this. Then these are the some band pass filter. So the center frequency is 60 and pass band is 20. Basically, I am filtering that. Okay, two times I am filtering it, and then I am once I filter it, so this will become a perfect sinusoidal wave, and that I am comparing. I am subtracting. So the error is coming here. That means the so this kind of harmonic filter, what it is doing, whatever the distorted area there, the necessary to make it complete sine wave, whatever the current is required, that is injecting. Okay, now you see I am feedback taking from the this inverter current, and that is compared with this signal, and then through a PI regulator. This is a PI regulator. This part is very important to set the value of this PI regulator. That is a how to tune that. That is a different thing. I am not discussing here right now. So this is a very simple thing. So let us simulate it and try to understand how change I. So this is the current in without filter, and this is with that inverter. Now you see the red color, there's a lot of distortion, but you see in that so this is just very quickly I have made for using further calculation. You can make this blue color line further smooth. Okay, so this red color line is the current, source current, without the filter, without that inverter or without the active filter, and this blue color is the waveform which is after incorporating the filter. Okay, now if you take the FFT also, you will understand there is a very you see this fundamental is, the fundamental will be at 50, but you see this is gradually, but in the red color there are lot of other distortion which is negligible, comparatively negligible in blue color lines. So this is basically all about your active harmonic filter concept. It's a very short, but it's a very big vast subject. So in your report what you can make, first you discuss about the general aspects of what is harmonic, and that first simulation in PCB and MATLAB, how you visualize the harmonics. You taken two different two signals of different frequency. Then you taken that data in a Excel file, and then you import it to MATLAB and did the and done the harmonic analysis. So this is the basic concept of harmonic. Then you talk about why this harmonic filtration is required, like electrical rotating machinery. This needs create sometime some harmonic, like odd harmonic, fifth and third. Those are creating the zero sequence. What I already explained during at the starting of this lecture. Then how to find out the harmonics mathematically, that is the Fourier series expansion, whatever I told already, this one. And then you come out talk about the passive harmonic filter. So it's very simple to design. It's a LC circuit where the resonance frequency of the LC circuit, it will be taken as um, uh, the harmonic frequency which you want to drain it. Based on that, the formula I have shown you, that omega 0 is equal to 1 by root over LC. So that whatever the formula I have shown you. So this using this you can explain the passive filter with the diagram, and for harmonic filter you can explain this uh, schematics, and using this that you can write the detail about the um, uh, passive harmonic sorry, active harmonic filter. Then you write a simple conclusion that this is what is this advantage, disadvantage, and its application and all, and you can conclude your report. Okay, so thank you so much. Hope with this you can prepare the report. uh, Once again, thank you so much. Thanks for your patience.